Hi, everyone. Just wanted to take a moment to talk a little bit about proofs. In particular, I wanted to give a general overview of what proofs are, and then show you a little bit about paragraph proofs, which we're going to kind of use as our precursor to the more traditional geometric two-column proofs. Um, but I felt this was a better place to start for us since we're a lot more comfortable with writing paragraphs and writing things down than we necessarily are using mathematical notation. So, anyway, to get us started, a proof in of itself is just a logical argument where every statement is supported by another statement that is true. So we break these into two different types of components. We break it into a statement, which is kind of what you're asserting, right? Those would be like what your claims are in your paper if you were writing a paper. Um, and then for each statement, you need to have a reason. All right. Um, and we're going to talk a little bit more about the reasons going forward, but each statement that you make needs to have a corresponding reason. You essentially have to spoon feed me all the information. I have to know that you really, truly are not making any giant logical jumps. I should be able to say A goes to B, goes to C, goes to D, goes to E, and so on and so forth until you get to what you need to prove. Um, and in general, what is going to happen is you are going to start with what you are given. So you're going to be given some information at the beginning, and that's your starting point. And you're from there going to use that information and anything you can derive from that information or other information that is widely known and accepted. And then you are going to, in the end, state what you are trying to prove. Okay, so that should be your final statement, and it should have a reason next to it. Okay, so you should start with what you were given, at least part of what you're given. You don't necessarily need to start with everything you're given. If you're given a couple things, you can start with just one or two of them. But you should then end with what you are trying to prove. That should be your last statement. I am blah, blah, blah is blah, blah, blah. And that should be whatever you are proving. And then there's a couple ways you can do these. This first way I'm going to show you is an informal method called the paragraph proof. Later on, we're going to get into some more formal methods. The largest and most commonly attributed and seen in this particular level of coursework would be a two-column proof, which is a formal, purely mathematical type of metric. But just because we're calling one formal versus informal should not denounce the credibility of one of the metrics. Okay, so a informal proof, as long as it still is encompassing, it still is a proof and it's still valid. All right. So let's look a little bit more into what a paragraph proof is itself. So basically, all you're doing is you're writing a paragraph mathematically to explain why a given conjecture is true. And I say mathematically and not an English one for the sheer fact of the matter that when you are writing in mathematics, I don't want anything extra. Nothing should be superfluous. No superfluity. I don't know if that's a word, but nothing should be extra. There should be no excess. It is simple statement, reason. The only other component that you might be putting in might be something to connect words together, like next or then. Statements like that, first, second, third. Those are acceptable, but that's pretty much the extent of any sort of fluff, if you will. You need to be using proper notation, and I understand that on a computer that can be kind of difficult to type out. But ultimately, you should be using appropriate notation. If you can't use the segment notation, like if you had A, B, and then draw the line, if you don't have the capacity to do that with whatever program you are using to type or write, then you should be instead writing segment AB, okay? So you can just, I will accept that. I understand it's not always the most convenient or simplistic to write, the line overhead. We can look at some of those as we go forward. But I know, like, for instance, trying to do it on Google Slides is significantly more of a pain than trying to do it in Google Docs. Google Docs is much better for typing, as you would probably imagine. But you should be using appropriate notation. You can't use what you're trying to prove as a reason. All right? I say that, you're probably looking at me going, well, that seems pretty obvious. And it's a very common mistake that is made when people are trying to do proofs. They end up using what they are trying to prove what they are trying to do. And it's just this circular logic that doesn't actually do anything. So you just need to be careful about that. And the final thing is, what is actually a valid reason or justification? So as before, we were saying we can make any statement, but we need to have a justification for it, which would be called a reason. And some things you can use would be definitions. If you have an algebraic property, we're going to spend a lot of time on the algebraic property, so don't worry. Postulates. So postulates are just accepted as true in the field of geometry. So they should, you can just use those. And then you can also use a theorem if it has been proven. And what I mean by that is you need to understand how to prove it in order to be able to use it. So once we have proven something in class, you are free to use it as a reason, but I shouldn't see you start using something from way down the line right now because you haven't proven it yet. So let's actually get into what we can do for a paragraph proof. So what we're going to look at is actually the paragraph proof of the midpoint theorem. So the midpoint theorem is a simple enough theorem, just stating if M is the midpoint of segment AB, AB, then segment AM is congruent to segment MB. And again, please be careful with the notation. So AB should have the line over it, AM and MB should have the line over it because we're dealing with the segments themselves, not their measures. And so we need the congruent. As an additional reminder, the definition of midpoint is that they are equal. So that's going to come into play when we are actually writing the proof. All right. So how do we prove that? Well, we can use a paragraph proof in this particular instance. So again, we're going to use this. This is essentially the same thing, except we've just replaced A and B with P and Q. So given that M is the midpoint of PQ, segment PQ. So right there, given that this is happening, this is our given information. This is what we know, okay? So that is the given. So that is where we are going to start. And we are also informed to write a paragraph proof to show that segment PM is congruent to segment MQ, which it does break you down here. But you can see right here saying show that this is what we're trying to prove. So this should be our final statement. We should be saying at the end, my statement is segment PM is congruent to MQ. And if we go back to the prior slide, you'll notice this is equivalent to the hypothesis and the conclusion. So when you are writing a proof and you're just given it in the conditional form of if P then Q, you're proving P, your given is your P and you're trying to prove your Q. All right, so this is what we were talking about with the logic tables. We're assuming P is true and we're using that to determine if Q is also true, right? So if we were doing logic, again, P is our given, Q, the conclusion, is our statement to be proven. All right, so let's break it down. What are we actually looking at here? From the definition of midpoint of a segment, the measure of PM is equal to the measure of MQ. So if we were to look at this, it's backwards in terms of what we were starting with, right? I told you we were going to do a statement and a reason. The way they wrote this, we have our statement here. Okay, so I have my statement. Segment, the measure of PM is equal to the measure of MQ. And that, the reason behind that, here's my reason. Again, we're just using writing convention, so it's okay if we put the comma and so on and so forth. The reason is actually given first, saying from the definition of midpoint of a segment. So all we're using here is the definition of what a midpoint is to justify our statement that the two segments are equal to each other in terms of length. All right. So our next thing that we can say we're just giving a little bit of more of a justification for it. This means that segment PM and MQ have the same measure. So all we're saying is we're just elaborating this a little bit more. We're just describing what this means. Honestly, this one's pretty self-explanatory, so you don't necessarily even need to use that sentence, but it's just included for extra clarity. By the definition of congruence. So again, we're using a definition. As a reminder, a definition is a reason. So we have another reason back here. So a reason of the definition of congruence. If the two segments have the same measure, then they are congruent. Okay? So we have a reason here, the definition of congruence. If two segments have the same measure, then they are congruent. That whole thing is a reason for our statement that PM, segment PM, is congruent to segment MQ. So all we're doing here is we only have two statements and two reasons, right? So we have our initial given. We are given that. So we did start with this. We use that information. That's our first statement. Our reason was that was given. Okay, so essentially statement one is always going to be given, and then the reason behind it is we were told that. Then we have another statement where we were using what we already know, right? We didn't just say this because we felt like it. We said this because we already knew it was a midpoint. So because we already had the information that was a midpoint, I was able to use this information to make a new statement, right? And it was justified by what we knew about the midpoint. And then finally, from that piece of information, just a step above, stating that it was a midpoint and therefore the measures were the same, we were able to use the definition of congruence to state what we were trying to prove, right? So really all you're doing when you're doing these types of proofs is you're looking at the information, and you can kind of sketch it out ahead of time in like a rough, if you just want to do like, statement, reason, given, what you're given, so on and so forth. You can just kind of sketch it out quickly, and then you can kind of just elaborate and put a few more words and make sure it's clear. All right. So this is essentially our starting point for proofs. And we're starting here again because I know you're a lot more comfortable and familiar with writing in mathematics versus just using simple the straightforward just notation and no words. That leap is a bit of a jump sometimes. So we're going to start with these. And let's just quickly look at one more. Okay. So this is a slightly different type of problem, but ultimately we're looking at a same kind of concept here, right? Angle 1 and angle 2 are vertical angles. That is what we are given, okay? That is just a piece of information that we know. So we can start with that. Now, we can then use a couple other pieces of information if we were to go through this process. So let's just quickly kind of sketch out in our mind what we're going to start with. We already know that things are given. Given that these two are vertical angles. And our ultimate goal is to actually prove that vertical angles are congruent. Fun fact. But let's see, what can we do to actually help with that? So what do we know about 1 and 3? Well, 1 and 3 are linear pairs, so we can use that. And what do we know about linear pairs? Well, linear pairs add up to 180. That's just what a linear pair is. 2 and 3 are also linear pairs, so they also add up to 180. And then, if two things add to 180, you can just set them equal to each other. And yeah, you'll be able to end up with 1 is equal to 2. All right. So that's just kind of a brief overview, and you might not even fully realize what I just did. But ultimately, this is kind of the process that you're going to be taking when you're doing the proofs. So again, we've already know that these are given. So from the diagram, angle 1 and angle 3 are a linear pair. Okay, so you can use the diagram in the other illustrations that you're given to justify your claim, right? If you can see that clearly something is true, you don't have to just ignore it. You can say that they are a linear pair from the diagram. That is perfectly acceptable. And I'm going to do another little shortcut here. As opposed to me writing from the diagram, 2 and 3 are linear pair again, I'm just going to say similarly, right? I'm saying by the same reasoning, essentially, when I use that. Similarly, angle 2 and angle 3 are a linear pair. By the definition of a linear pair, the measure of angle 1 plus the measure of angle 3 equals 180. I'll just use similarly again. Similarly, the measure of angle 2 plus the measure of angle 3 equals 180. All right, so we've gotten to this point where we said the measure of angle 1 plus the measure of angle 3 is 180, and then the measure of angle 2 plus the measure of angle 3 is 180. So what are we going to do now? Well, we can set them equal to each other. And how can we do that? This is essentially just the transitive property. If A is equal to B and B is equal to C, then by the transitive property, A is equal to C, right? So by, I'll just say transitivity. I'll get fancy. Transitivity. The measure of angle 1 plus the measure of angle 3 is equal to the measure of angle 2 plus the measure of angle 3. Through, what are we going to do? We're going to subtract 3 from both sides. So through subtraction, all right, and if you want to be more specific, you could say the subtraction property of equality, but you can just say subtraction. Through subtraction, the measure of angle 1 is equal to the measure of angle 2, right? It's very clear. You just subtracted 3 from both sides. They canceled out. You're left with the measure of angle 1 plus the measure of angle 2. And now what are we going to do? Same kind of argument that we used in the last one by the definition of congruence. By the definition of congruent, and you know what, I'll be even more specific. I'll say by the definition of congruent angles. You can say what things you're calling congruent. You could have just said congruent. I would have accepted that. I understand what you meant. By the definition of congruent angles, angle 1 is congruent to angle 2, right? So what did I just end with? I ended with what I was trying to prove. I started with the fact that they were vertical. We knew that piece of information in the diagram. I used the piece of information in the diagram to say that things were a linear pair, because you can use the information presented to you in the diagram. And then I logically walked through it, right? We said they were linear pairs, so what does that mean? That means they add up to 180. What does that mean when that they both add up to 180? Well, we can just set them equal to each other. When we can set them equal to each other, we can subtract things from both sides through subtraction property of equality. And then ultimately, that just leaves us the measure of angle 1 is equal to the measure of angle 2. There, we already used a similar argument in the last proof that we did. We said that by the definition of congruence, in this case, the definition of congruent angles, the two angles were congruent. Thus, we were proving what we were trying. We had proved what we were trying to do. And the best and most fun part, to indicate you are done, you can do one of two things. You can either do a little square. Sometimes it's filled in. I can like to fill it in. And then you could also do QED, which is a Latin phrase, which we'll talk a little bit more about going forward. But if I don't want to screw it up yet, I want to double check and make sure I say it correctly before I say it on video. So I'll talk about it more next time. Have a great night.